Hello, this is Dusty Jones here to talk about some ancient methods of calculating. The origin of the word calculate in English comes from the Latin word calculus, which comes from the Greek word calyx, both of which mean pebble. That's probably because early calculating methods involved the use of small objects like pebbles. And calculation was necessary just for basic counting and enumeration, in terms of finding out how much property a person had or money, as well as having an accurate calendar and keeping track of time. In this presentation, I'm going to talk about finger reckoning, the use of the abacus, and in general the use of tables. First of all, finger reckoning, or calculating with your fingers. Initially, body parts were used to enumerate items, that is, pointing to the littlest finger or the wrist or the elbow might denote a different number. The Latin word digitus literally means finger, and it's where we get our word digit from, which can refer to your fingers, but can also refer to the numerals 0 through 9. The monk Venerable Bede described representing numbers up to 10,000 on the fingers and numbers up to 1,000,000 by placing the hand on various parts of the body. Using this method of placing the hand on various parts of the body, such as the elbow or shoulder or index finger, helped facilitate trade in the Middle Ages, especially when language was not common, and the notation was fairly uniform up to the number 100. One way to use fingers to multiply, say for example when the factors are between 5 and 10, you can hold up the number of fingers that are more than 5 for each factor on separate hands. So for example, if we're looking at 8 times 6, we put 3 fingers up on one hand and 1 finger up on the other hand, since 8 is 3 more than 5 and 6 is 1 more than 5. We add the fingers that are up, which makes 4, multiply that by 10 to get 40. Then we look at the fingers that are down. We have 2 down on one hand, 4 down on the other. Find the product of those down fingers. 2 times 4 is 8. And then we add the 40 from the up fingers to the 8 from the down fingers to get 48. So therefore 8 times 6 is 48. And why does this work? Well, if you have, let's say, A fingers up on your left hand and B fingers up on your right hand, the remainder of the fingers, assuming you have 5 fingers on each hand, the down fingers are 5 minus A on the left and 5 minus B on the right. And this method's going to tell us what 5 plus A times 5 plus B is. That is, A is the up fingers, so that number is representing 5 plus that for the first factor. The up fingers, in part B of the method described previously, takes the sum A plus B and multiplies it by 10. And the multiplication of the down fingers is 5 minus A times 5 minus B. And we can use some algebra to show that 5 plus A times 5 plus B equals the sum of A plus B times 10 plus the product of the quantities 5 minus A and 5 minus B. A similar method exists for when the factors are between 10 and 15, although we only use up fingers in this case, and the fingers up represent how much that factor is above 10. So in this picture I have 13 times 11, 3 fingers up and 1 finger up. We still find the sum of the fingers that are up, and that makes 4 times 10 is 40. Then we do the product of the up fingers. 3 times 1 is 3. And we take the 40 and the 3 and add that to 100, and we get 143. So we say 13 times 11 is 143. Now let's talk about the abacus. The abacus is the earliest known device used for carrying out mathematical operations. We get the name for abacus from the Greek abak or abakion, which is really a board that was really dirty or strewn with sand or dust. And this sand table, this abacus, was used for drawing figures. Later on, pebbles were used in computation, perhaps with a clean table. Even after that, the abacus became a table that had grooves in it and some counters or pebbles. The Roman abacus was like this. And also, just for your information, the Roman abacus not only had grooves for whole numbers, but also for fractional parts. An abacus like this was also used in the Orient as early as the 500s AD. In China, it was called suanfan, and in Japan, it was known as the soroban. The soroban is still used today, and like other abacuses have become, they're now, instead of grooves, there are beads on wires. That keeps them from being lost, I suppose. The soroban has two panels, a lower panel and an upper panel. There are 4 beads on the lower panel and 1 on the upper panel. The upper counter has a value of 5 times as much as any counter on the lower. So if we look at the very right column, those are the 1s on the lower panel and 5s above. The second column, those are 10s on the lower panel and 50s on the upper panel. The third column is the hundreds in the lower panel and 500 in the upper panel, and so on. So here on the soroban represents 4,637. The 600 comes from a 500 and a 100, and the 7 comes from a 5 and 2 ones. The abacus is very useful for computations, especially in numeration systems that weren't well suited for written computation, such as the Greek numeration system. It's very difficult to compute in Greek using written numerals, but the abacus made it very easy. Early textbooks included instructions for computing with the abacus, as well as using a written algorithm. Sometimes the written algorithms were placed in the back of the book, maybe if you were good enough to get there. And in the Middle Ages, there were big debates between people who advocated using the abacus and people who advocated using written algorithms over which was better. To add using an abacus, you represent the first addend on the abacus and then place in the second addend, and when you have too many for that column, say you're on a soroban and you have more than 5, you take 5 of those 1s and place it as 1 5 above that. Or if you have 2 5s, you can replace that with 1 10. This may be where we get the term carrying, from carrying a pebble from one column to the other. The disadvantage of using an abacus for any computation is it's difficult to check without recomputing the whole thing. You can't really go back and see what happened because each step you do kind of erases the previous step. To subtract on the abacus, you represent the minuend, the first number in the subtraction statement, and then you remove or erase the subtrahend. If you need to take from one column, say you need to take a 10 away from the tens column and replace it with 10 ones in the units column, that may be where we get the term borrowing. I now want to talk about multiplying and dividing using tables, specifically Egyptian and Babylonian tables. The Babylonians used tables for products and reciprocals, at least as early as 2000 BC. And these tables were used so that people didn't have to keep multiplying. They could just look up the product on a table. Of course, their numbers were represented sexagesimally. They didn't list a table from 1 through 59 on the top and going down the side, but they just used certain numbers. They used 1 through 19 and then 20, 30, 40, and 50, and multiplied those across the top and down the side. To find a product of some number that was not on there, say 43, they would use the distributive property, actually looking up the product of 40 and 7, and then 3 and 7, and add them together to find the product of 43 and 7. And so here I have those. 40 times 7 is 280, which is 4 60s and 40 left over. 3 times 7 is 21. And so when we add 4 comma 40 to 21, we get 4 comma 61. However, that 61 is too large for the 1's place value. And so we move 60 of those to the make 160 and get 5 comma 1. Babylonians used reciprocals to divide, and so rather than divide by 6, they would multiply by 1/6. Some reciprocal tables that they had used only what I'll call regular sexagesimals that had finite sexagesimal form. They probably didn't deal with the repeating sexagesimals. So usually those were denominators with factors of 2, 3, or 5 in the prime factorization. So for example, the reciprocal of 6 is 1/6, or in sexagesimal notation 0 semicolon 10. And 15 divided by 6, it would be the same as 15 times 1/6, or 15 times 0 semicolon 10. 15 times 0 is 0, and 15 times 10 is 150. And then we can regroup that 150 into 2 60s and 30 leftovers, which comes out to be 2 semicolon 30. The Egyptian multiplication tables used a table of 2 divided by n, where n was an odd number from 3 through 99. And these tables were used for multiplication. A question I'm not going to answer, but I will ask, is why do you suppose they didn't include even numbers for that denominator, 2 over n? Throughout history, multiplication tables were used. Nicomachus of Gerasa wrote an influential book, Introductio Arithmetica, in 100 AD, and included a multiplication table up to 10 times 10. That doesn't seem like a big deal to us because by 4th grade we've all made these tables, but it was a big deal the first time it came out. Some Italian merchant arithmetic books often gave tables with products not of all numbers but just primes, some up to 47 times 47 and some up to 97 times 97. And possibly to find a product that was not prime, they would use the prime factorization. A mathematician named Krell wrote a very influential book in 1820 in which he provided a multiplication table for all integers between 1 and 999. And that is one of the most valuable aids in computation before computers and modern computing machines were invented. There were division tables. They did exist, but they were less common, and the values for the numerator and denominator, or the divisor and dividend, rarely exceeded 100. And also tables existed for square roots, cube roots, trigonometric function values, and logarithms, and all of these were very common until all of this information was able to be extremely condensed into a calculator.